So I have started the recording and good afternoon everybody. Today is our 16th lecture of the course and we have started discussing arrays yesterday. In particular, we have looked at defining integer arrays and we did a some simple things about printing the address of elements of the arrays, how to access elements of the arrays and so on. And one particular task that we did, which was possibly something which was interesting to you, was printing out the histogram of the marks of quiz 1 for our class. So we did that using a simple program where we did not store the marks of the students in an array, but actually that the range of the, we had an array for the range of the marks, that is 0 to 20, and we counted those and we saw a few things about small corner cases about the program. So anything that was unclear or something that you want to ask about yesterday's class? Okay, so what we are going to do is go back to these real life problems that we are interested in. Let's say today we will take the first problem, which is the evaluation of a polynomial. And then we are not going to go to this encrypt and decrypt messages, which requires us to define character arrays. We are going to spend some more time on integer arrays before we move to character arrays. So we'll do a few more examples of integer arrays itself in today's class. Okay, so let's get started with the task of evaluating this polynomial. So as we said yesterday, there are many reasons where we have to evaluate a polynomial, and we'll not get into where this is useful, but this is useful at many places. Here, our task is that we are given these n+1 coefficients, which is a0, a1, a2 up to an. So these are n+1 coefficients. And for the moment, in today's class, we'll assume that they are integers. They can be real numbers, but we'll assume that they are integers. We want to evaluate this polynomial a0 plus a1x plus a2x squared up to an x to the power n at a particular value of x, which is also an integer for us. Again, it can be a floating point value, but that will just change the type of the variable. But other than that, it is the program will remain the same. The thing is that we, in many cases, it may be required that the user has different values of x in mind at which the user is going to give us, the user wants us to evaluate this polynomial. However, the coefficients, of course, don't change because this is the polynomial is defined by these coefficients, and therefore these coefficients don't change. So what we are going to do is going to store these coefficients in an array. And these coefficients, we are going to use them, and we are going to use them to evaluate the polynomial. Okay, so there is some question. Somebody has a question? Yeah. So the user provides all the n+1 coefficients. So it is a0 to an, right? So there are n+1 coefficients. So the user provides n+1 coefficients. What is the question? In fact, we will allow the user to provide the degree of the polynomial also, but that is apart. So that is a small thing. Okay. Okay, good. So let's get started with writing a very simple program for this and then see whether we can do any modifications to this program. So is the question clear? Are there any queries about the task that we want to do? Okay. So this is the simplest program that one can one can come up with this for this task. So observe the following, that we have included this math.h, which you may have included in some of your assignments earlier, and we'll see the reason why we have included this math.h. X is the variable. This is the formal variable for which the user is going to provide us a value. As we said, we are going to have this as an integer. n is the degree of the polynomial. We are going to take this as an input, and I is running index for us. So this is something that we are going to run over from 0 to n. And we are going to store these coefficients in an array, which is an integer array. And we have said that the max degree is limited to 20. So this is something which is an assumption. Yesterday's program, remember that we had this size of the array defined as a constant integer. In this program, I have kept this as a constant here. Again, it will be a good practice for you to have a constant defined, or later on when we define using what is called as hash defines, we'll use hash defines also. But this is something that you need to keep in mind. Then this value is something that we are going to initialize to 0, in which the answer will be stored, and in this value we are going to finally compute the value of this polynomial. So we are scanning n and x in that order, and then of course we are also scanning the coefficients. Each of the coefficients is scanned, and as we scan the coefficient, we are doing the following. That is, once you have the coefficient, let's say a0, which is the first one which will be input, then you are multiplying it with power of xi. So this is a function. POW is a defined function which will return x to the power I, and this is present in math.h. That is why we are actually including math.h. And this will give you x to the power I. So the first time I is 0, so it will give you x to the power 0, which is 1, and therefore it is just a0. Once you have a1, this will give you x to the power 1, which is x, and so on. And then you are simply computing the polynomial as you are given in the formal form. So you are computing it from left to right in this way. Is the program clear? Is there any error or anything that is mistaken about, or there is a mistake in the program, or anything that is not clear? Should the loop run from 0 to n? Should it run from 0 to less than n? Any errors here? Okay, so I assume that this program looks correct to everybody. So I want all of you to do the following. That is, I want you to tell me how many multiplications does this program do. This is nothing to do with coding. You have to analyze this program and tell me how many multiplications does this program do. So just think of that. Whenever there is a multiplication done, you are incrementing the count of some variable, or you are counting it, or there is somebody who is counting, so or charging you 1 unit for a multiplication. So how many multiplications is your program doing? So count that and tell me how many multiplications is it doing. So I see that all of you are writing it in your chat messages. So when I say multiplications, it is all the multiplications that are done by this program. Think of it, whenever you call the multiplication operator, it is going to charge you 1 unit. Wherever it is in the program, it is going to charge you 1 unit. Okay, so I see some of you have responded. I'm very, this thing that I have not been able to use the poll function, which poll here, which allows us to see how many people have responded. But yeah, I see quite a few responses. And the common responses that I have, I mean, there are 2 distinct responses that I have. One is n plus 1, which is there. and the second is slightly a larger number, so I'll come to it. So let's look at the first obvious answer, which is n plus 1. So this n plus 1 is coming because this loop is running n plus 1 times, and there is a multiplication operation which is done here, and therefore the answer seems to be n plus 1. So this is the answer that is given by many of you. There is also another common answer that is given, which is n into n plus 1 by 2, and this is the answer which is given by people who have observed that this power is something that we have written and we have abstracted out several multiplications. So every time there is a power that is being used, we are you are of course multiplying. So when you say x to the power 0, of course there is no multiplication. X to the power 1, there is no multiplication, but x squared and so on, there will be 1 multiplication, 2 multiplications, and so on. So this is something where we are doing several multiplications that are not counted by the simple analysis when you look at how many times does this loop run and there is 1 multiplication operation that is happening here. So is that clear? I mean, n plus 1 is not the correct answer. So we'll come to the correct answer, but n plus 1 is only a lower bound. It is saying that we are doing so many, but there are more number of multiplications. Okay, so before we go into the number of multiplications, there is one question which is relevant, which is related to the coding part, and I will answer that. So one of you has asked this n, so I have said that the degree of the polynomial max degree is 20, and I have said coefficients is equal to, coefficient is an array which is an array of size 20. So one of you, I think Nanda Gopal, has asked, can I say that I declare a variable n and fix its value equal to n? In fact, there is no need to declare another variable n. You have declared this little n, which is the degree of the variable. Once you have scanned it here at line 9, you can move this statement which is at line 6, or the declaration of the array which is at line 6, and say int coefficient COEFF of n, little n in this bracket, and that will work. I just want to try this annotation and see if it works. Just give me a moment. So what Nanda Gopal is asking is, or suggesting, is this, that we can also
Ma'am, I have a doubt. Like, can we actually say that? Can we actually declare int array of some variable? Shouldn't we use a constant variable? That's what I was suggesting. Like,
no. So that is what. So it is not required. So I'll just answer your question. Just give me a moment.
okay.
So okay. So his suggestion or question is like this: that can we have the following statement here? Int coefficient. So don't worry about my writing, but of n. So I hope you can read, all of you can read this, of n here, and n is the variable. I'm sorry. Yeah, so this is the statement. I hope you can see it, that I have defined, I have used this variable n, which was not
Yes,
defined as
ma'am.
a
Actually,
constant
it should be
integer.
n plus 1. I made a mistake because we need all from 0 to n. So we have
Yeah,
to set.
okay, n plus 1. Okay,
Yes.
so good. Okay, n plus 1. But let's say that the user gives 21 if the degree is 20, or 5 if the degree is 4, and so on. But the point here is not about that n plus 1. The question is, can we write this statement like this, which I have written here, which is the int coefficient n, where n is a variable, and that is a valid statement in C. In the current compilers, that the current compilers do support such statements. However, yesterday's class we had said this earlier, right, that an array is a fixed, the array size should be fixed and finite. So this was true in the earlier versions of C. However, in the current version, the GCC compiler will allow you to write such a statement. That is, you scan the value n here, and then you write this int coefficient. So you declare an array which is having its size as a variable, which is taken as an input from the user. So this is something which is allowed. So it need not be constant, integer, and so on. It need not be a constant. It can be something which is taken from the user.
Okay.
Is that clear?
Yes, ma'am.
Yeah. Yeah. But at that point, whatever is the value of that n, the array size will be given that much memory, right? Or the array size will be of that value. N can of course change later, right? And you can modify n because n is not a constant variable. So is this clear
Yes,
to everybody? We were on a slightly different discussion, but this is also important. I wanted to bring it up possibly later, but this is good. So yeah, so this is something which is allowed by the compiler, and you will be using that. So okay. Okay, so having said that, let's move to our original discussion where we were saying that okay, so where we were counting the number of multiplications that are done by this program, and as we said, n plus 1 is not the correct answer. We'll have to see how many. So let's look at this carefully. So when we are evaluating this term, which is a n into x to the power n, to compute x to the power n, we are doing so we are doing n minus 1 comparisons, and finally this multiplication an into x to the power n, that itself is taking the last not comparison, sorry, multiplication. So these are n multiplications, so that is the n that I have written. Then the penultimate term here will have n minus 1 plus n minus 2 and so on up to 1. So this will sum up to roughly n into n minus n into n plus 1 by 2. So this is something that will be the number of comparisons. Of course, there can be a plus 1, minus 1 here and there, but it is roughly n squared number of not comparisons, sorry. Please excuse me for saying comparisons repeatedly. It is multiplications that we are doing in this program. So are there any questions here? Yes, so you are right actually. So one of you has pointed out coefficient of 0 into power of x to the x0, which is 1, will be a 1 multiplication. So that is what we have counted here. So yeah, as I said, there can be one multiplication that you can save possibly by writing a program in a different way. But as long as you write the program in this way, there will be roughly n squared multiplications, which is n into n plus 1 by 2. And of course, there are n additions that are there, which we are doing. So we have these roughly n squared multiplications and n additions. And at lot of places you will see that multiplications or these basic operations are some things that you will want to optimize. So here we are asking this question. This is nothing to do with our coding, but it will have an impact on how we write the code. Is can we improve this and get the multiplication slightly better? Can we do this and improve these number of multiplications, or get down this number of multiplications? Assume that you are charged for every multiplication, and that is why you want to get these multiplications down. So just take a minute and think about, can we improve these multiplications? When we say improve, we want to get these multiplications as small as possible.
Ma'am,
Yes.
what do you mean by getting multiplication as small as possible? Like the
Yeah, so can we write a program? I mean, so currently we have written a program in which roughly there are n squared multiplications and n additions. Do you agree with that?
yeah, yes, ma'am, yes, ma'am.
Yes. So is there a different way of writing this program, or writing it in a different way such that the number of multiplications that our program does is smaller than n squared. If we have that, then think of it that you are paying a unit amount to every time you do a multiplication, your program will be paying lesser, right? Is that clear? I mean, we want to, so we have just done this analysis that this is doing n squared multiplications. Can there be a program which does the same thing but does fewer multiplications?
Okay, I get it, man. I get it.
Yes, okay, good. So as I said that it is not something to do with immediately with coding. It is more of analyzing how to write a program better. You can think of it in the same spirit as GCD. And it will of course lead to faster programs. Not that we can see the difference immediately, but in general it is desired to have fewer number of basic operations. Okay, so again, many of you have given this suggestion that this use of power, which seems very nice because okay, anyway there is a power function, let's use that. Of course, note that if you try to use this program as it is, the way I have written and compile it, of course compile. But when you want to create an executable, you will have to use the math library. So you will have to link it using the -lm. And then it will run correctly. So this program is correct, but you should use -lm to link the math library. Only then the executable will be created. So, but more than that, I mean, this power function is abstracting it out, and that is why it is also misleading us. Earlier, many of us said that there are only n+1 multiplications, which is not true because we are hiding away our multiplications in this power function, or the use of the power function. So many of you have suggested the right thing to do. That is, can we instead not use the power function and write a program without our power function, which also does better in terms of the number of multiplications. So let's read this modified program. So it is fairly same, except that I'm also having something which is a factor which I have defined, which is initialized to 1. And initially I am multiplying the coefficient. I mean, I am always going to multiply this coefficient with my factor. And this factor is going to take care of having x to the power I at every point. However, I am not going to call this power function because the power function starts from scratch. Instead, when I have computed x, when I am in the loop for I is equal to 4, in the previous iteration I must have computed x to the power 3. Why don't I reuse that? So my factor already had x to the power 3, or in fact when I enter this loop when I is equal to 4, I will make sure that my factor contains x to the power 4, because I'm at the end of the loop, I'm going to change my factor is equal to factor into x. So I use the factor first. That is, when I go into the loop, I use my factor first, which is containing x to the power I. But just when before ending the loop, I'm going to change factor is equal to factor into x. So at the end of the loop, it contains x to the power I plus 1. When I'm in the loop for a particular value of I, right? So therefore, instead of computing x to the power I from scratch, which my earlier program was doing, this program does not compute this power from scratch, but reuses what was done in the previous iteration, and therefore it hopefully reduces the number of multiplications. So okay, so now first of all, let's ask whether this program is correct. Are there any mistakes in this program? Okay, is there anything that is incorrect? Is factor containing the correct value, or is it off by 1, off by 2? Okay, any thoughts whether it is correct or not? I mean, does it seem right? Okay, math.h is not required. I agree. This is a copy from the previous this thing. So math.h is not required. But again, that is not an erroneous part of the program. Yeah, but yes, it is not required and it can be deleted. Line 2 can be deleted. I agree. Okay. But apart from that, in terms of the logic or in terms of the loop indices or anything that is there anything erroneous in the program? So now let us now ask how many multiplications does this program do? Okay, so the question that Srivas has is, it calculates x to the power n plus 1. Hold on. So just before you answer, so Srivas, can you tell me how many, why do you say it calculates x to the power n plus 1? It does calculate x to the power n plus 1 in this last thing, but yeah, it does calculate that. But does it calculate the polynomial correctly or compute the polynomial correctly? Because when I becomes n plus 1, it is not going to enter the loop. So it is not going to change anything in the value. Is that clear? So this last multiplication can be avoided. Is that what you are saying? I'm not clear. Okay, so Srivas, can you unmute yourself and speak up? I am not able to. Okay, so I don't know whether Srivas is there or not, but how many multiplications do we do? Again, many people are now writing their answers. So this program is doing far fewer multiplications. The earlier program was doing n squared multiplications, roughly n squared multiplications. This program is doing something like 2n multiplications, again plus minus 2, but in fact it is. So this goes into the loop n plus 1 times, and every time you do 2 multiplications. So therefore it is 2 times n plus 1, which is the exact number. But again, when n is a very large number, these small factors are something which are less importance. But we have come down from n squared to n by doing this small modification to the program. So this was saying that, I mean, use of some functions which will make the code look modular and good is fine. However, it can be expensive in terms of your running time of the program or the number of basic operations that it uses. So you have to be careful about even such simple programs where you can optimize on the number of multiplications that your program does. So yeah, so this is something which is one learning from this small exercise. But we are going to do a little more. So before we go further, are there questions about this way of writing or evaluating the polynomial? Okay, so Ashwin, right? So we need maximum degree. If we need maximum degree equal to 20, we need 21 coefficients. Okay, yeah, agreed. So I should not say maximum degree is 20. There you have 20 coefficients. I agree. So this is a wrong comment. I should say maximum degree is 19. Then we will have the number of coefficients is 20. Thank you, Ashwin, for pointing this out. I should change this in the slide. Okay, I agree with your comment. Anything else about the multiplications? Okay, so so what we have seen is that by a small observation, we have improved our number of multiplications significantly. Let's not stop here for this and do a little more, which is not this. I mean, which is not an immediate idea, but which is something which can be observed and if you rewrite the polynomial in a different way. So this is in fact called as the Horner's rule of evaluating this polynomial. So note that I have the polynomial that we are familiar with. I have written it here in blue, and the same polynomial I have written it in a slightly different way, which is saying that I have just put in brackets appropriately. So it says x into an plus an minus 1, all of this into x. So this is actually x into an minus 1 plus x squared into an, but it doesn't stop here. So in fact, there is a x here again, and so on and so forth, as long so that actually you are multiplying an with x to the power n as required, a1 with x, a2 with x squared, and so on. So this is just a rewriting of this polynomial in a different way. There's nothing changed. It is, please stare at it and make sure that you see that it is exactly the same polynomial, but it written in a different way. Now, we would like to see whether this rewriting of the polynomial helps us in writing code which will allow us to further reduce the number of multiplications that we are using in our program, right? So is this rewriting okay with everybody? Okay, so what we want to achieve is roughly n multiplications and n additions. Of course, these n additions are something that we are not changing anywhere, but we are trying to reduce the number of multiplications. So what I have done is, this is the same piece of code that you are familiar with. I want you to write down this piece of code here, where assume that you have scanned the coefficient, so that part is done for you. You have n and x, you have the array defined appropriately. Assume that your degree is small, it's 4 or 5 or 6, something that doesn't make you worry about this 20. So you have the coefficients correctly stored, and you are going to have them from 0 to n, and n is significantly smaller than 20, so you don't have to worry about that, the corner case. So you have to fill in the code here such that it evaluates your polynomial in this rule, the way I have written it here, so that it actually kind of is in line with this way of writing the polynomial. So please try to fill in these lines of code, and if possible, write it in the chat message also.
Okay, and this code is slide which has the codes, which is the code, man.
Sorry?
Can I just go to the slide which has the code, man? Code.
Yeah, so I will go to the code slide. I mean, I think that slide is slightly less interesting than this writing of the polynomial. I wish I had both of them together, but there's nothing. So there, you just need to know that coefficient is an array of size whatever you want appropriately, which contains from 0 to n the appropriate coefficients, and you can define your own variables, but value should contain finally what the value of the polynomial is. And of course, x is your formal variable, which is an integer which will take the value which is given by the user, and n is the degree of the polynomial. Okay, so Rahul, you have written the answer, but yeah, okay. So note that n is something that we are not changing. Our loop index was I, so it would be good if you can use it using your variable I instead of changing n. That is again a suggestion. You can of course change n. There is nothing holy about that. Yes, you can do this using a single loop in the program. That is correct. Okay, so people who are writing the scanf, etc., please don't write the scanf of the coefficient and so on. That is already written for you. So that is not something which is the interesting part of the code. I want you to again go back to this slide where I have written the polynomial in a different way, and it is, yeah. So just for students who are possibly stuck at this thing, so I request all of you to write down the polynomial in your notebooks or your text these things so that you can see the polynomial written in this way in front of you. And I not only will give this part of the code, but I'll write a little more for you so that you are, you are in fact, there is a little more hint for you that maybe you should go from n down to 0 and try to compute this value instead of going from 1 to or 0 to n. Note that all the coefficients have been collected for you already using the scanf, so you are not collecting the coefficient or reading it on the fly. You have already collected the coefficient from the user, so all of the n coefficients are available to you. So although you may have written correct answers in the earlier parts, please, I request you to fill out this line 16 now rather than filling out other things. So please fill out just this line 16 with the knowledge that we already have value is equal to coefficient of n as the initialization instead of value being equal to 0. And we are running our loop from n minus 1 all the way down to 0. So what will the value be? So again, I don't know why some of you are writing it as a of I and so on. There is no other array variable array that we have defined. There is only one array, which is the coefficient array, which we want to maintain. Okay. Okay, so yeah, okay, so some of you have said that, okay, A is the coefficient array, that is fine. Please use the same variable so that we have the same answer that we have. Yeah. So this is more or less like your exam questions that we have been asking you. So you just have to fill in. So there is almost one answer, or there is only one way to fill in this last line, given that you are given all of this here, right? Okay, so in the interest of time, let me fill up this fill in the blank here. So what it says is value is equal to x times the value plus the coefficient of I, right? So the coefficient of I is going to be something that is remember that we are running the loop from n minus 1 all the way up to 0. So initially we had value is equal to coefficient of n. This x into value is kind of shifting it and multiplying it by multiplying it by x repeatedly, the way we want it in this the way we have done it in this writing of the polynomial. And then it is further adding, so this is the x into part which it is doing, plus it is adding the earlier coefficient, sorry, so not this one. So sorry, this x into an is something that it is doing, plus an minus 1, which is this part. Once you have computed this part in the bracket, when you enter the loop in the next time, your value contains this part in the bracket, and you are going to multiply it with x and then take the penultimate coefficient, which is an minus 2, and add it to it, and so on. So next time you enter the loop, your value contains this, of course, without the x, and then you multiply it with x and continue doing this, right? So this is exactly how this polynomial has been computed using the way it is written using the Horner's rule. So this is one way to finish this piece of code. There may be small variations to this, but more or less it has to be this. Once you have all of this set value has been set equal to coefficient, and the loop is run from n minus 1 to all the way to 0. So any questions in this part? So now
I have
the question. Yes, sure. Yeah.
Ma'am, what I had done was I'd written value as coefficient of 0. And my loop ran from 0 to 1. And my incrementing thing was values equal to, in brackets, value plus coefficient into x.
Yeah, so as I said, right, if you don't have this loop here, right, you can have if you don't have your loop running from n minus 1 to 0, or with the earlier slide, your answers may be different, right? Because you will have to, you may have different answers, but remember you should, I will have to check your answer. So maybe you can send your answer and then I can, sorry. So Sri Lakshmi, right? So I'm not saying that this is the only way. You can write the loop which is going from 0 to n, that is okay, or 1 to n, that is fine. But your body of the loop may be slightly different, and I will have to look at your body of the loop if you have a different way of writing it. So you can send it to me. I will look at it, but if your loop is running from n minus 1 to 0 and the coefficient value was set to coefficient of n, then more or less this should be the answer. So there are different ways of writing this if you write the loop in a different way. Does it answer it?
Yes, ma'am. Thank you.
Yeah. So I don't know for sure whether your current loop is correct and the inside statement in the loop is correct, but you can send it to me and I'll look at it. Right? Okay. So now before we end this discussion, I want you to observe how many multiplications are we doing here. Yeah, so now we have come down from 2n two times n plus 1 multiplications to n multiplications now. Of course, we could have also saved one multiplication in the previous code by checking whether, because we are computing x to the power n plus 1, so I agree with that. But roughly 2n multiplications to n multiplications is what we have achieved, not by doing something very great in coding, but observing that our code written earlier was not utilizing what was computed in the previous iteration. That was the first thing. The first big step that we did was getting rid of power, which was repeatedly computing power x to the power I from scratch. So we got it from n squared to 2n, and then from 2n we further got down the number of multiplications to n, and that this seems to be something that we'll now settle down for. We have n multiplications and n additions, and one can of course ask, is there something that you can do better? In this case, no, but this is a valid question that you can ask, that can we do even better and do something which is fewer multiplications. So what are our learnings from this exercise? That the first attempt solution itself was correct. Of course, there can be minor things about that 20 and so on. Those are not about the writing of the or the evaluation of the polynomial, more about the comment that I had given. But the first attempt was correct, but it was improved in terms of the number of multiplications from, again, roughly n squared to 2n to n, which is a significant improvement, and it did not require anything very difficult, but it requires thought before you start coding or while you are coding, and then you observe these things and you can continuously refine your programs to make sure that they do optimum, not only in terms of your coding that you are doing, but in terms of the way the code is written. So I think this example is in very much spirit with the GCD problem that we have seen, where we went from a simple algorithm to simple method to this Euclid's method, which gave us a significant improvement in the running time. So okay, so so the initialization of the array should be, oh, so I think Shwetika, right? So what is the question? The initialization of the array should be coefficient of 21. No, so it should not be coefficient of 21. In fact, n is the degree of the polynomial, right? So you are going to have it in n. So the coefficient, the an is sitting in coefficient of n. Is that clear? It's not sitting in coefficient of 21. 21 is some maximum value, which assume that we'll never achieve that, or it is a large array that is given to you. Is it fine? So Shwetika, does it answer your question? This initialization is not incorrect, coefficient of n. because we are saying n is the degree of the polynomial.
Ma'am,
Is
can you
that
hear
fine? Yes.
like for the scanning part, ma'am, like generally arrays, like if it is a coefficient of 20, then we'll have from 0 to 19 only, right?
That is correct, 0 to 19. So that was pointed out earlier, right? That the maximum degree cannot be 20. It should have been 19. Yes.
Okay, ma'am. So if it is 20, then it has to be 21, right?
Yes. I agree with that, that this is an incorrect comment here, and that I mentioned too, or in the next slide when we were discussing. This is an incorrect comment. But assume that, I also said that let's assume that the degree is 4, 5, 6, 7, something which is significantly smaller than 20. Let's say less than 15. Then all of this is still correct, because n is something which the user is providing, which is the degree of the polynomial. So we are initializing value with coefficient of n. Is that okay?
Yes, ma'am. Understood.
Sure. Okay. Any other questions or comments? Okay, so having done this, we can move to a slightly different set of problems on arrays, integer arrays, which are again very important and heavily used when we are doing anything that we are doing in real life. Searching and sorting is something which is like the heart of anything that you do in programming, or when you start doing with the computer. Even when you are searching files, you have to do control F, search your files, or find and do something. So searching and sorting is, I mean, these are some things which are very fundamental to anything that we are doing with the data, and therefore a lot has been invested in coming up with good sorting algorithms. Specifically, searching of course has its limitations unless you have some nice structure on the input, and we are going to see that. But so what we are going to spend time on for this class, which is the remaining part, and tomorrow's, not tomorrow's but day after tomorrow's class, is on learning these searching and sorting techniques for integer arrays. And while we will learn this, or we'll see this for integer arrays, this will apply for character arrays and so on as well. So I just want to understand from you before I get started, what techniques have you seen searching and sorting earlier when you have learned programming? Again, these will be samples that you will answer. I mean, I'll take samples from you and see what is the general this thing. So yeah, just don't say yes, but what are the searching techniques that you have seen? What are the sorting algorithms or techniques that you have seen? Okay. Okay, so I am getting answers which say that you have seen searching and sorting. You have seen linear search and binary search. You have seen selection sort, bubble sort, and even merge sort. Okay, and insertion sort, many of you. Okay, so then I think I can be quite fast in this, and we can quickly cover ground in this, because many of you have seen this. Okay, so just hold on now, so I get a good sense. So okay, so there is Gokul. Is it possible to get a break for 2-3 minutes? So okay, is this break required for you, Gokul, or is it okay? So is this the general feeling that this 75 minutes class is a very long class and you need to have a break? So do other people also feel that you need a break? Okay, so maybe we'll take a break here and get back after a few minutes. So maybe 2 minutes or something. Is that okay, or you want 5 minutes break? Okay, so I'll stop here. I'll be just here. I don't want to leave the. Yeah, I think 10 minutes is a very long break because then we lose class time. So I won't give 10 minutes break. Sorry, but let's say we'll just wait for a few minutes. If people have some things to say about anything that they want to talk about, which is not directly related to this class, but possibly something that will help me plan for future, you can discuss that, or if you have any comments or suggestions. Yeah, I'll wait for a few minutes and then start the class again. I think, okay. So let's get to searching and sorting, and we will restrict our discussion in today's class to searching and sorting in integer arrays. But the same kind of programs or the algorithms that we are going to talk about will be useful in character arrays and I mean other arrays that you are interested in, and of course when we go to other data types as well. Okay, so so let's start with the very basic problem that we are given any integer array. So this integer array is written down for you. So it has 3 plus 3, 6 plus 3, 9, 10 elements. So this is an integer array of size 10, which is indexed from 0 to 9. And we want to search an element. So this search element is typically called as a key element. So we'll call this as searching a key in this array, and this key is given to us. Key is nothing but another integer which we are interested in finding out whether this integer is present in this array. The typical search problem is a yes or no, but we will augment it by saying that we would like to return the index at which it is present in the array. And it doesn't matter if it is present multiple times, some index at which it is present is good enough, right? So this is something which is the search problem. Since most of you have at least seen the problem, this is not something which is unfamiliar. So there's not too much to say about the problem itself, but so we are saying that there is this integer key which is given to us. I have not written the statement which says scanf key, but it is given by the user. So the key is something that we are going to take from the user. I've also not written code which says that A is an array which is an integer array of size 10 and it is appropriately initialized either by the user in the program or you have taken input from the user. That all that I have not written, but when you are at this place before the for loop, your initialization is for the array is done and the key also has been initialized by the user providing you the key, right? So we want to know whether this key is present in the array, and it's a very simple program. It just runs, you just run the loop from 0 to n minus 1 because n is the size of the array. So the array indices run from 0 to n, 0 to n minus 1, and you are going to only check if a of I is equal to key. If it happens, a is the array that we have defined, int a which is of size 10. And if it is found, then if it happens to be the key, then we have found the key, and therefore we will say that we have found the key at the index I. And as soon as we find the key, there is no need to go further into the loop because we just want to find one occurrence if it is there. And if it is there, we are going to break out of this loop. Therefore, as soon as you find the key, you don't need to go further, you break out of the loop. So this doesn't tell you how many times the key occurs. If it occurs multiple number of times, it gives you the first occurrence of the key going from left to right. Again, you can ask, give me the last occurrence, give me the total number of times the key occurs in the array and so on. And this program can be easily modified. So this is the basic search algorithm, which is called as the linear search in an array. And this is something which will work on all arrays. Given a key, you can always find an occurrence of the key if it is present using this simple loop which just tests for every element in the array whether it is equal to the key. If it is equal to the key, then it breaks. Otherwise, it just otherwise it keeps on searching as long as it has not found the key. And if it does not find, then you will never write this statement. So you may want to write that the key is not present, but this program is not writing that. If it is not present, it just doesn't say anything, it quits silently. So any comments or questions here? Okay, so just like what we did in our analysis in the previous program, that this is this linear pass, can you avoid this in case avoid this for a general array? So that is what is the metric that we want to optimize? Just like in the previous program, we said that we are interested in minimizing the number of multiplications. Here it is the comparisons that you are interested in looking at or counting. So whenever you are comparing something, so think of it that this is an equality operator that you are using. You are paying or less than or greater than, or whenever you are saying ai and a of I and key, you compare them either for less than, greater than, or equal to. You are going to pay something, pay 1 unit, any of them, less than, greater than, less than, equal to, greater than, equal to, you are going to pay. So every time you take these two elements and compare, you are going to be charged something. So you want your charge to be as small as possible. So we want to know how many comparisons are you making and can you reduce the number of comparisons. So this program or this piece of code, which is the linear search, is going to make n comparisons, because if the key element is not present, it is going to compare it with every element in the array, and declare that it is not present. Can you avoid this? Can you avoid this comparison? If, I mean, every element is being compared, can you avoid this in general? Okay, so this cannot be avoided unless you have some structure on the input, and if the input is sorted, then you can indeed do better, much better than what is done in this linear scan. And that is what we are going to see, because many times the input is sorted, or if it is not sorted, it may be in our interest to sort the input, because the search happens so many times that it may be better for us to optimize the number of comparisons that are done. And so can you tell me real life examples where you do searching in a sorted array or sorted something? It's not an array, but searching in the sorted something. So real life examples where you do this. Okay. Okay. I'm happy that people are looking up dictionaries in paper, I mean pen and paper. I thought everybody looks up on Google, so you don't get this thing of searching in a sorted array. But yes, when you are looking up words in a dictionary, or if some of you have looked up telephone numbers in an old directory, then you are actually searching in a sorted array, or something which is sorted already. So I don't know whether you people have actually looked at telephone directories which used to be there. And I have actually as a kid looked up in the telephone directory where those were alphabetically sorted, and we would look up phone numbers of people whom we wanted to contact. Yeah, so there are many places where you will need to do searching in a sorted array. Nowadays, we are not doing it manually. That is why we don't encounter it. But the computer does the task for us, and it internally sorts it to make the task of searching easier for us, right? So many times we will have either a sorted input, or we will sort the input ahead of time, and then we are going to do a searching in the sorted array. So let's look at this special case where we are going to do searching in a sorted array. So I have now sorted this array, and I have sorted this in a particular way. Doesn't matter. It is sorted in decreasing order here, but we will call it a non-increasing order because we don't know whether the elements are going to be distinct. So we have sorted it in a decreasing order or a non-increasing order, and we are going to be given a key that we want to look for. So what is going to be our strategy? It is a very natural thing that we know how to do. We are going to uh, we are going to take any element. In fact, why any element? We are going to take a middle element, roughly the middle element, doesn't matter. If you have the, if you, since many of you said dictionary, you must be used to this opening the dictionary at any point, see whether the letter of interest has come in. If you are lucky, great. If not, then you are going to check whether you should go to the first half of the dictionary or the second half, and that depends on what is the letter on the page that you have opened relative to the word that you are trying to search. So the same thing we are going to do here. That is, if the we are going to check the middle element. If the middle element happens to be our key, great, we are lucky and we will break our search, or we are going to get out of the loop that we are having. Else we decide which part of the array is relevant to us, and if that part, and depending on which part of the array is relevant to us, we are going to only focus on that part which is relevant to us and search in the left or the right part of the array, just like what we do for a dictionary or a book, sorry, a telephone directory that we are searching a name for. So this is what is called as a binary search, because we are going to divide our input or the array into half every time, and we are going to concentrate only on one part of the array to do our search. So yeah, so just take a minute to absorb this. I'm going to look at what are the questions here. Yes, so the question, that one of the questions is, can we have duplicate entries in the array? Yes, you can have duplicate entries in the array. We have not forbidden that there are no duplicates in the array. Is there a particular thing that bothers you, Gokul? I mean, why is this? Why do you think that if you have duplicate entries, there can be issues? Okay, so I do not I don't see any other questions which are relevant to this. I mean, no questions. There are other comments. Okay, so given that we have this kind of a thing that we want to do, that is, we want to check the middle element. If it is found, if the middle element happens to be the key, so assume that we are having the key as the variable which will contain the value that we want to search. And this is something that this is the method that we are going to use. So let's assume that we are having this array, which is the array of size 10, and explicit numbers are here. And let's say that we are going to search for the element 6, which is not present in this array. So what I want you, all of you, to do is tell me, according to this, which indices are you going to probe and check when you are going to search the element 6, which is not present in the array, right? So if this is your method, you are going to take the middle of the array. So you should tell me which indices you are going to probe and check, right? So all of you calculate that. This 32 is sitting at index 0. This 3 is sitting at index 9. Therefore, there are 10 elements in the array, right? So all of you calculate which are the elements that you are going to probe. Okay, so one of the questions that one of you has is there how will it improve the complexity if we are sorting first and then searching? So note that we are not trying to improve the, so it is not said that we are going to sort. I mean, that is correct, that if we sort it, then we are spending more time. But think of it that you are getting 1,000 searches into an array. Then every time you are doing, if you do linear search, you are going to spend 1,000 comparisons, whereas you do sorting, you are going to do one time sorting and then you are going to do these 1,000 searches. So many times it is helpful for you to sort, but at the moment we are not saying that you sorted. In fact, you are saying, our title says searching for an element in a sorted array. So we assume that it is sorted for us. right? So of course, nobody is going to give you a sorted array, but typically it is, the search happens so many times that so building these indices, right? Google, whatever it has done much more than sorting. I mean, sorting is just a very, very small thing. We are doing these searches regularly. It is like just as natural as waking up, doing our regular tasks. Much more than that, we keep searching on Google. Google has built this huge indices, which is much more than sorting, but they have built it one time, and all of us are using those indices to uh, get things or search things efficiently. Okay, so is there something that is to, yeah, if you want to know the length of the array, you can say that length of the array, you can think of, there is a function. It is not required, but yes, you can assume that there is a length of the array which is there. But note that the length of the array will give you the length of the original array. So you need to do the bookkeeping. I'm not asking you to write code for the moment. I'm just asking you what indices will be probed. Okay, so one of you has written what indices will be probed. I will wait for a few minutes for, I mean, at least 1 minute for others to tell me the answer. Note that it is the indices that you should give me. Based on that, of course, we can find out the values. Okay, we are looking for the value 6 that we are searching in this array, which is not present. So we are looking for the value 6 and it is not present in the array. So I would like you to tell me what indices are searched. Okay, so let me again try to annotate this. I hope it works slightly better. Okay, so I again have, so please don't give me these answers about n by 2 and all, because n by 2 doesn't make sense. You have to tell me explicit answers about what indices are going to be searched. So the indices can be 1, 7, 15. 15 cannot be there because this is an array which has 0 to 9. So, okay. Okay, so I don't get too many answers, although people have said that they have looked at binary search. Okay, so let's do what we agreed to do. That is, we are going to check the middle element. The middle element here happens to be 4. That is the index 4 that is here. So we are going to check whether the value of A of 4, which is 15, is it equal to our search key? So the search key in this case is equal to 6. So we are searching for 6 and we want to know whether 6 is present in the array. Of course, 6 is not equal to 15. But we also see that 6 is less than 15. So it must lie in this part of the array. And therefore, there is no point in going to this part of the array because 6 is strictly less than 15. So it won't be present in the left part of the array. Therefore, it is okay to concentrate on the part which is marked on the right side, which starts from the index 5 and goes all the way up to this index 9. Right, so this is our interest area now, which is the part of the array which is relevant to us, has been marked out here. So now our array, although the array has not shrunk, but the interesting part of our array has shrunk from being from the index 5 to 9. So this is the index 5 and this is the index 9. So this is the interesting part of the array for us now. So just give me a moment. Okay, so I'm unable to erase this part, but it doesn't matter. So this is the interesting part of our array. We are going to now look at this part and see that for this part, we are going to go to the middle of this. what is the middle of these 5 numbers? This is the middle of these 5 numbers. So therefore we are going to okay, so we had checked this index. Then we know that we want to check between this and this. So the middle of this is this index that we are going to check, which is this is 5, 6, 7. So after we have checked this 4, we are going to check this index 7 that we will check whether 6 is equal to the key that we are interested in, which is this 6 is equal to a of 7, which happens to be 8, which is not there. So we realize that we are going to still go to the right part of the array and check out. Now when we have these two elements, we will still have to look at the middle of this, and we will check the middle, which happens to, I mean, again, there is no middle that is there. So we are going to check this element, which is at index 8 and which happens to be 7. Then we are again going to check whether 6 is present or not. It is not present. Therefore, we know that we still have to go to the right of the array. So we are going to have to check again the last element, which is at index 9. And therefore, we are going to make these 4 comparisons, which is 6, 7, 8, and 9. And these are the 4 comparisons that we will make if we want to find the element, which is 6, which is not found in the array. Is this clear to everybody? So the elements that are probed are ones which are marked here. Yeah. So 4. Yeah. So this is here. This is not something which is checked. So it is 4, 7, 8, and 9. These are the indices which are marked. Anybody else has a different answer? Anybody has a different answer here for this 6 itself? So am I audible? Yeah. Can somebody confirm that you can hear me?
Yes, ma'am.
Okay,
Yes, ma'am.
okay, sure. Okay, thank you. Yeah, so now I hope you see what we are doing when we are doing this binary search. So I would like some of you to tell me how would we write this code for binary search. We are almost done with our time. So I just want you to tell me how do we write. I'm not going to show the code. When we come in on Thursday, we'll again revisit this, and we will revisit binary search and write down the code for that. But maybe while just as an ending thing, if you know how to write the code, you can tell me how you are going to write the code. Yeah, you can type out your chat messages. Also, I mean, people who possibly have seen this or forgotten this, but have forgotten this, may want to think about is, till now for all our programs in this class today, we have been very nicely using the for loop. Is there another loop construct which is more suited for this binary search program that we are interested in writing? Okay, so I think maybe it is not fair to ask you to write down, because people are writing down check mid, check key, and so on. So it's fair that we go over this program a little slowly. So yeah, and people have written that while loop is something that will be more appropriate. So we look at this program carefully. Although it is a very simple piece of code, it is something that requires a thought to write it correctly. So we will revisit this when we come on Thursday. So the class the class is over. We'll come back to this on Thursday. Okay, thanks to you all. I'm going to stop the recording now.